I'll give one more example. This is a North Pole. This is a South Pole. So here I will take a loop. Let it be suspended. I'm showing the loop, you see. There's a loop, or you better say iron plate, conducting plate. No, I'll deflect it. So as it deflects, so what will happen to the motion of the plate here? Will be damped oscillations or undamped oscillations? How the lines of force? The lines of force should be in this direction. I can deflect in either way. No? So I think I just shown the direction. Try to, I think I'm unable to, this is a 3D situation. No? And the plane of the loop will be parallel to the plane of bar magnet, this particular surface. The plane of the loop will be parallel to this tangents or parallel to the plane of this edge of the bar magnet, this side of the bar magnet. Is it okay? No? This one. So I'll displace it. So it will oscillate with its plane perpendicular to magnetic field. So I'll put like this: iron plate oscillates with its plane perpendicular to magnetic field of bar magnet. Magnetic. Okay, now try to see. What is the type of oscillations it will be? Damped oscillations or undamped oscillations? Will be damped oscillations. So I think I'll just show a plane diagram. This is a loop. How the B bar will be will I agree this? So when the loop is in this position, when the loop comes to this position, so look at now, a part of the loop will flux linking that will change. So what about here? Eddy current will flow here in this region. Similarly, when the loop is here, now an eddy currents will flow in this region. So this eddy current, what it will do? It will, the retarding force will be set up. So when the loop is, when entering or leaving, there'll be retarding force. So there'll be a velocity like this here. Then how the retarding force will be like this. When it's having velocity in this direction, then how the retarding force will be like this. This retarding force will decrease the amplitude of oscillation, will be damped oscillation. This is the one thing. And now, if the iron plate is so aligned, I'll displace it, I'll align it such a way that if the plane of the loop, so everywhere open, iron plate oscillates with its plane perpendicular to magnetic field. If the iron plate oscillates with its plane tangential to magnetic field, tell me what happened to eddy currents. Will it be there? Between the bar magnet spacing only, it will oscillate here. So what is the oscillation now? Damped oscillations are produced by plate. Okay, next question comes from why the damped oscillation? Because of the eddy currents, the retarding force is set up that will decrease the amplitude of the plate as it enters magnetic field and leaves that one. Or means say like, sir, what about the field due to bar magnet? In fact, it will be non-uniform. I'm just showing it uniform. if it's a non-uniform, everywhere when it's moving, what happens? The flux link will continuously change and damped oscillations will be generated. And now, if the iron plate oscillates with its plane parallel to magnetic field, tell me what will happen in that case. No eddy currents. Any reason for that? Because the B bar will be tangential to plate, flux linking the loop is zero, and will be undamped oscillations. I'll show the diagram in this way here. So now if the B bar, there's a B bar, and if there's a plate, blue color will take it. In this case, I think there won't be eddy current, no? Am I right? In any position, not only, sir, in any position you would draw it. You have to be very careful. In exams, there won't be support for you through the diagrams. Huh? Please, you have to really understand the content, the limited content what they give. No eddy currents because B bar is parallel to tangent. Strictly what happened? Plane of the plate is tangential to B bar. So flux linking the plate is zero. No EMF induced. So no eddy current.